US Physics Olympiad, year 2019, USAPHO, final round. This examination consists of two parts. Part A has 3 questions and is allowed 90 minutes. Part B also has 3 questions and is allowed 90 minutes. Problem A1. Collision course. 2 blocks A and B of the same mass are on a fixed inclined plane, which makes a 30 degrees angle with the horizontal. At time t equals 0, A is a distance L equal 5 centimeters along the incline above B, and both blocks are at rest. Suppose the coefficients of static and kinetic friction between the blocks and the incline are μA equal √3/6 and μB equal √3/3, and that the blocks collide perfectly elastically. Let VA and VB as functions of time be the speeds of the blocks down the incline. For this problem, use G equal 10 meters per second square. Assume both blocks stay on the incline for the entire time and neglect the sizes of the blocks. Question A. Graph the functions VA and VB for t from 0 to 1 seconds on the provided answer sheet with the solid and dashed line respectively. Mark the times at which collisions occur. This is the answer sheet. Question B. Derive an expression for the total distance block A has moved from its original position right after its nth collision in terms of L and N. Now suppose that the coefficient of block B is instead μB equal √3/2, while μA equal √3/6 remains the same. Question C. Again, graph the functions VA and VB for t from 0 to 1 second on the provided answer sheet with a solid and dashed line respectively. Mark the times at which collisions occur. Again, this is the answer sheet. Question D. At time t equal 1 second, how far has block A moved from its original position? US Physics Olympiad, year 2019, USAPHO. Problem A. Green revolution. In this problem, we will investigate a simple thermodynamic model for the conversion of solar energy into wind. Consider a planet of radius r and assume that it rotates so that the same side always faces the sun. The bright side facing the sun has a constant uniform temperature T1, while the dark side has a constant uniform temperature T2. The orbit radius of the planet is R0. The sun has temperature Ts and the radius of the sun is Rs. Assume that outer space has 0 temperature and treat all objects as ideal black bodies. Question A. Find the solar power P received by the bright side of the planet. Hint: the Stefan-Boltzmann law states that the power emitted by a black body with the area A is sigma A T power 4. In order to keep both T1 and T2 constant, heat must be continually transferred from the bright side to the dark side. By viewing the two hemispheres as the two reservoirs of a reversible heat engine, work can be performed from this temperature difference, which appears in the form of wind power. For simplicity, we assume all of this power is immediately captured and stored by windmills. Question B. The equilibrium temperature ratio T2 over T1 depends on the heat transfer rate between the hemispheres. Find the minimum and the maximum possible values of T2 over T1. In each case, what is the wind power PW produced? Question C. Find the power PW in terms of P and the temperature ratio T2 over T1. Question D. Estimate the maximum possible value of PW as a function of P in one significant figure. Briefly explain how you obtain this estimate. US Physics Olympiad, year 2019, USA PHO, final round. Problem A3. Electric slide. Two large parallel plates of area A are placed at x equals 0 and x equals d, which is much less than square root from A, in the semiconductor medium. The plate at x equals 0 is grounded, and the plate at x equals d is at the fixed potential negative V0, where V0 greater than 0. Particles of a positive charge Q flow between the two plates. You may neglect any dielectric effects of the medium. Part A. For large V0, the velocity of the positive charges is determined by a strong drag force, so that V equal mu E, where E is the local electric field and mu is the charge mobility. Question 1. In the steady state, there is no reason but time-independent density of charges between the two plates. Let the charge density at position x be rho x. Use charge conservation to find the relationship between rho x, Vx and their derivatives. Question 2. Let Vx be the electric potential at x. Derive an expression relating rho x, Vx and their derivatives. Hint. Start by using Gauss's law to relate the charge density rho x to the derivative of the electric field Ex. Question 3. Suppose that in the steady state conditions have been established so Vx is proportional to x power b, where b is an exponent you must find, and the current is non-zero. Derive an expression for the current in terms of V0 and the other given parameters. Part B. For small V0, the positive charges move by diffusion. The current due to diffusion is given by Fick's law, I equal negative AD multiplied by d rho over dx, where d is the diffusion constant, which you can assume to be described by the Einstein relation, d equal mu kbt over q, where T is the temperature of the system. Question I. Assume that in the steady state conditions have been established so that the non-zero steady current flows and the electric potential again satisfies V proportional to x power B prime, where B prime is another exponent you must find. Derive an expression for the current in terms of V0 and then other given parameters. Question B. At roughly what voltage V0 does the system transition from this regime to the high voltage regime of the previous part? US Physics Olympiad, year 2019, USAPHO. Final round. Problem B1. Strain in the membrane. The wall of a neuron is made from an elastic membrane which resists compression in the same way as a spring. It has an effective spring constant K and an equilibrium thickness D0. Assume that the membrane has a very large area A and a negligible curvature. The neuron has ion pumps that can move ions across the membrane. In the resulting charged state, positive and negative ionic charges is arranged uniformly along the outer and inner surfaces of the membrane, respectively. The permittivity of the membrane is epsilon. Question A. Suppose that after some amount of work is done by the ion pumps, the charges on the outer and inner surfaces are Q and negative Q, respectively. What is the thickness D of the membrane? Question B. Derive an expression for the voltage difference V between the outer and the inner surfaces of the membrane in terms of Q and the other parameters given. Question C. Suppose that the ion pumps are first turned on in the uncharged state and the membrane is charged very slowly, quasi-statically. The pumps will only turn off when the voltage difference across the membrane becomes larger than a particular value V. How large must spring constant K be so that the ion pumps turn off before the membrane collapses? Question D. How much work is done by the ion pumps in each of the following situations? Express your answers in terms of K and D0. Case 1. K is infinitesimally larger than the value derived in part C. Case 2. K is infinitesimally smaller than the value derived in part C. US Physics Olympiad, year 2019, USAPHO. Final round. Problem B2. Stellar black box. Scientists have recently detected a new star, the MAR Kappa. The star is almost a perfect black body, and its measured light spectrum is shown here. The total measured light intensity from MAR Kappa is 1.12 multiplied by 10 power negative 8 watt per square meter. The mass of MAR Kappa is estimated to be 3.5 by 10 power 30 kilogram. It is stationary relative to the Sun. You may find the Stefan-Boltzmann law useful, which states the power emitted by a black body with the area A is sigma A T power 4. Question A. The spectrum of wavelengths lambda emitted from a black body only depend on h, c, k, b, lambda and t. Given that the Sun has a surface temperature of 5778 Kelvin and peak emission at 500 nanometers, what is the approximate surface temperature of MAR kappa? Question B. The lines in the spectrum result from atoms in the star absorbing specific wavelengths of the emitted light. One contribution to the width of the spectral lines in the Doppler shift associated with the thermal motion of the atoms in the star. The spectral line at lambda equal 389 nanometers is due to helium. Estimate to within an order of magnitude the thermal broadening delta lambda of this line. The mass of a helium atom is 6.65 by 10 power negative 27 kilogram. Question C. Over the course of a year, MAR kappa appears to oscillate between two positions in the background night sky, which are an angular distance 1.6 by 10 power negative 6 radians apart. How far away is MAR kappa? Assume that MAR kappa lies in the same plane as the Earth's orbit, which is circular with a radius 1.5 by 10 power 11 meters. Question D. What is the radius of MAR kappa? Over the course of some time, you observe that the star's intensity periodically dips from I to 1 minus 10 power negative 5 I, and then rises back to I with a period t. One possible explanation for this observation is that exoplanet is orbiting the star and blocking the starlight for some time. Question E. Estimate the exoplanet's radius, assuming that it is much closer to the star than to the Earth. Question F. Assume the exoplanet is a black body with a uniform temperature in a circular orbit around the star. What must T be so that the planet has a temperature of 250 Kelvin? If this were true and the planet had an appropriate atmosphere, the temperature would increase enough to support life. US Physics Olympiad, year 2019, USAPHO, final round. Problem B3. Pitfall. A bead is placed on a horizontal rail along which it can slide frictionlessly. It is attached to the end of the rigid massless rod of length r. A ball is attached at the other end. Both the bead and the ball have mass m. The system is initially stationary, with the ball directly above the bead. The ball is then given an infinitesimal push parallel to the rail. Assume that the rod and the ball are designed in such a way, not shown explicitly in the diagram, so that they can pass through the rail without hitting it. In other words, the rail only constrains the motion of the bead. Two subsequent states of the system are shown below. Question A. Derive an expression for the force in the rod when it is horizontal, as shown at the left above, and indicate whether it is tension or compression. Question B. Derive an expression for the force in the rod when the ball is directly below the bead, as shown at right above, and indicate whether it is tension or compression. Question C. Let theta be the angle the rod makes with the vertical, so that the rod begins at theta equals 0. Find the angular velocity omega equal delta theta over delta t as a function of theta.